These are the frames to write for unrestricted.
You're all set?
Yeah.
Oh, are we good to go? All right, so good afternoon, everyone. Thanks for coming to the AstroAI lunch half. Today, I'm happy to introduce Aryana Haghjoo, who's a grad student, second year at UC Riverside, working on the Washer group. We've had some very good interactions with people from that group, so it's great to have you here. We met at the AstroAI workshop actually, and then again at NIRSpec. And Aryana is going to be telling us about using machine learning to do super resolution of low resolution galaxy spectra with applications of galaxy evolution. So the floor is yours. Please, as always, feel free to interact with questions or comments. And other than that, please go ahead. Thank you so much.
Hi everyone, thank you for coming. As Rafael said, I'm Aryana Haghjoo. I'm a second year PhD student at UC Riverside, and before that, I was a master's student at McGill University. And today I'm going to talk about the super resolution project. This project is a collaboration between our group at UCR and the group of Shubhana Kanmati at Caltech IFAC. So we're going to start. First, let us revisit why do we actually need high resolution spectroscopy. High resolution spectroscopy is a modern, central modern diagnostic for astrophysics. It helps us deblend emission lines individually, and with deblending those, we are able to measure the line fluxes, the profiles, fluxes, and line ratios correctly. And these observed line ratios are the basis for many physical diagnostic tests we need to do with these galaxies. In contrast, if we only have access to low resolution spectra, the survey scale, approximately resolving power of 100 to 300, we lose a lot of this information because of this resolution, and therefore all of the downstream information that we extract from this resolution, this low resolution spectra, is going to be to have higher error bars. Having access to high resolution spectra also gives us access to accurate redshifts. And with this accurate redshifts, we can have better cosmological analysis, such as galaxy clustering and big cleansing studies. Also, if we have access to high resolution spectra, we can have precise measurements of physical quantities, physical characteristics of the galaxies, such as the SFR ratio, the star formation rate from the H-alpha line, the dust attenuation rate from the Malvern decrement, the gas phase metallicity, the agent activity and population studies from the DPT diagram, the electron density from the S2 line ratios, the shock is stellar wind and outflow from the O1 line. This one is specifically such a weak line, and also the kinematic studies, the rotation curves and velocity dispersions. Many of these measurements depend on the very well resolved lines, such as H-alpha or H-beta and O3. And we know that these lines are close to each other in the wavelength space. So if we have access to only low resolution, these lines are going to be blended together. So our measurements of those physical quantities is not going to be very exact, because the fluxes of these lines are blended together, and we don't have access to the individual fluxes. So you need high resolution spectra to have a very good measurement of these quantities. With that motivation, let me walk you through the outline of this talk. I'm going to talk about the challenges that we have for acquiring high resolution spectra for a very large sample, and the opportunity that the use of AI gives us to reconstruct the lost resolving power. Then I'm going to talk to you about the actual work that we did, the data set that we used, the data set from the JWST, and how we pre-processed that data set, then how we augmented that data set to make it ready for our training architecture, and finally, I will show you the results of this method, and more importantly, the evaluation methods that we use to make sure that these generated spectra are physically correct and meaningful. So, I hope that by now you're convinced that we need a large resolution, a large sample of high resolution spectra. So we need this, but acquiring high resolution spectra is a very time consuming and observationally expensive task for our telescopes. So we can't have a large number of samples observationally. That's why modern deep surveys such as Euclid and Future Roman telescope are only focusing on acquiring a large sample of low resolution spectra compared to getting some just focus on some individual objects for high resolution spectra. And this is a major information bottleneck, as we discussed. Most of the physical diagnostics that we need are not going to be very exact by only focusing on the low resolution spectra. And the main motivation behind this project is actually to address this information bottleneck. So how we can solve this problem with AI? If we have access to a sample of the data that has both low resolution and high resolution spectrum, like paired samples from the same galaxy, then we can train an AI model to learn the mapping between these two. And then using that inference that we get from this training, we can then feed the low resolution spectra from samples that we don't have the high resolution spectra for, and then use that inference to predict the super resolved spectra. As I said, an example of this low resolution spectra can be low resolution prism spectra from Euclid and Roman telescope. Now, let me tell you how what kind of data we use and what kind of challenges we had in terms of preparing this observational data for the training. So we use the JADES data because JADES data has both the low resolution resolving power of approximately 100 and medium resolution resolving power of approximately 1000. The low resolution prism one is the red one here in this diagram. And the high resolution one comes in 3 different patches. It's the green, blue, and black ones here. This data set focuses on the good north and good south fields, and it's a deep field data set, meaning that it has both very faint and very bright galaxies. So it gives us a very diverse training set. However, the problem is that because the medium resolution spectra doesn't come completely out of the box and it comes in 3 different patches, it has some kind of gaps in the region that we're interested in. We're mostly interested in the 1 to 5 micrometer region. So we have some gaps here, and we also have some overlaps. And we need to address this and merge these data sets before we can use it for training. So the first task was to merge the 3 medium resolution gratings. And then we had to also regrade the low resolution to the grading, the wavelength reading of the high resolution spectra, because we didn't want to lose any resolution in the down sampling process. So we brought the low resolution to the high resolution grading, basically using a very simple interpolation method. And then we also needed to apply some quality cuts, because we wanted to make sure that it feeds a spectra to the model that doesn't have any emission lines. We don't have this problem that the model will predict false emission lines. And in order to prevent that, we introduced a quality cut, basically only keeping spectra that have detected the alpha O2 or O3 lines with an SNR of over 5. And then after this quality cut, we will remain with approximately 1,200 pairs of data sets, which is obviously not enough for a very healthy training. So I will answer this question later, how we solve this method. But for now, so this is the only observational data. So the biggest observational data set that we had access to that had this kind of the pairs that we needed, the pairs of low resolution and high resolution. And this is a sample from our dataset. It shows how these 2 different resolutions give us completely different physical information. The blue line here is the line from the prism resolution, our result power of approximately 100. And as you can see, the 3 H beta and the 2 O3 lines are completely blended together. However, in the green line, which is the resolving power of approximately 1000, all of these three lines are blended very quickly. And that's our goal for the super resolution model as well. So, as I mentioned, we only had 1,200 pairs of data, and that was not enough. So we had to do augmentation. And the way we did it, we had to completely invent our own augmentation method because we couldn't find a reliable one for one-dimensional data. It is quite obvious for two-dimensional data sets, but not exactly straightforward for one-dimensional data. So in order to also remain physical, we introduced redshift perturbations. We derived redshift perturbations from a random offset. And then we also added a little bit of Gaussian noise, approximately 10% of flux value at each point. And therefore, we were able to make 20 copies of each of the observational spectra that we have. And therefore, the size of our sample size went from 1,200 to approximately 25,000. And by doing so, we effectively increased the diversity of our data set in terms of line positions, shapes, and also signal to noise ratios. And as you can see here, the black line is the actual observational data, and the rest of the lines are the 20 copies of the data set that we created to increase the size and diversity of our data sets. So what kind of training we use? We explored many different architectures. We explored just one simple CNN. We explored diffusion models. However, the one that worked best for us was a three-step model, basically three different networks that inherit information from each other. The first one is a very conservative super resolution network. It's a CNN architecture, and it does the super resolution tasks, but it stays very close to the low resolution spectra. Again, just to make sure that we don't hallucinate information that are not physical. And then a second CNN predicts the redshift based on the results of the first super resolution. And then by having that redshift, we can now focus on windows in the wavelength region that we expect to see a spectral feature such as emission lines or absorption lines. And this layer is an attention layer, and it's a transformer base. So we focus on those regions, and now we are able to give a finer prediction. So this one is no longer staying close to the low resolution. It now stays closer to the high resolution target. And in order to make sure that this model is having its best performance, we fine-tune the hyperparameters using the baseline biases tool. And finally, this model was successful to recover the emission lines and the deblended features that we needed. Now, let me show you the results and evaluations of this model. So here, the purple one is a target high resolution, and this red one, dotted red one, is the low resolution input, and our prediction is the orange one. And if we zoom on one of the regions, for example, the region of the 203 lines, as you can see in these two examples, in the prism spectrum, they were completely blended together, and we were able to recover them deblendedly in our generated super resolution spectra. The first evaluation method that we used was looking at the residual maps of this spectra. Here, the y-axis on this plot is all of our evaluation sample is stacked on top of each other, and we are looking at the residual map of between the low resolution and the high resolution spectrum. As you can see, it has a very clear structure to it, the red-blue structure. And these lines that you see here are the emission lines, because we stack these evaluation samples on top of each other in order of the redshift, so we can see the emission lines very clearly. And again, we can see that if we compare the low resolution to the super resolution, we again have a very, very obvious difference, meaning that the super resolution is not staying close to the low resolution. And finally, if you look into the comparison between the super resolution and the high resolution, you can see that we don't have that obvious structure anymore. and the residuals seem like a Gaussian. The Gaussian has a higher flux in lower wavelength regions. However, in lower wavelengths, we also have higher observational error. So this is kind of expected. This is not a problem, but
sorry for interrupting. I'm still thinking about your architecture. So you say you have three steps.
yes.
The first step is just a convolutional layer that tries to predict the high resolution spectrum from the low one. Then you have a second network that predicts the redshift.
Yes.
That's based on what? What's the input to that second network?
The super resolved spectrum from the first network.
Okay. And then the third one, it's a transformer.
Yes.
That is trained to do what exactly? So what do you pass as an input, and what's the objective of the transformer training?
So the objective is a super resolved output, and the inputs are the super resolution from the first network, and also the predicted redshift from the second network. So because it has the redshift now, it can understand what region is what is spectral, because it knows the redshift.
And the objective is just a sort of reconstruction of them.
To focus on that, we know that for example, know that H alpha is here. The transformer has attention on that window.
Okay.
Since you're already expecting to say on microphone?
No, well,
They're not working, unfortunately.
I have two quick questions. First of all, you said you augment by redshifting. Then do you have to patch the ends somehow?
But we do cut the ends. We cut them between 1 to 5 micrometers.
Right, but when you have that, you have extra.
You'll see I cut them, yeah.
And then have you tried the Spectra? There's this redshift invariant encoder. Just for some what's the name? Spencer?
Spencer, I think. Yeah.
I'm not familiar with that, but
Because since you're predicting the redshift, then to get rid of that, but you have all different redshifts in your data set before you, right? Okay, yeah. So
the diversity is not that much of a problem before training, because it already has like local galaxies up to redshift 10, something like that. The issue is more with the size of the data set.
Yeah.
Because 1200 is just not enough, you know.
But your model should be agnostic to the source, right? So your model is learning the convolution of the instrument with the spectrum, right?
Yes.
So why not take all of JWST's like data that has a high resolution and low resolution? Or is JADES the only one that's doing this?
It's the biggest dataset that we found that was doing this. There is another dataset called the Void GTO that actually uses our high resolution here is actually the medium resolution from the NIRSpec instrument. NIRSpec instrument also has a higher resolution, resulting from 700 to 3000. But the dataset from that one is much smaller. It's like 1200, 200, 300, etc. So this JADES one was the biggest that gave us this pairs of.
Just maybe for someone else. So actually, I made the mass square wide survey. We have like 5,000 spectra of them. I think the key thing is that only JADES tested 140 ends.
Okay.
So it has like all three just for
Right.
Yeah, because there is an idea that if you have like a high resolution, why don't you just computationally lower the resolution and then train from that? But because we use a function to do that, to decrease that resolution, the model is going to learn that function very quickly. It's not going to learn the physics, it's just going to find out that function. So we wanted to make sure that our low resolution data is also an observational data.
But the model is just learning the convolution, right? I mean, there's nothing physical about the convolution.
The resulting power of the telescope has some physical data to it because it is wavelength dependent. It's not just one simple function.
Right, I was going to ask about, when you augment the data, do you account for the fact that the resolution changes very rapidly?
Not in this model, but in the work that I'm going to talk about it later, but in the work that we're currently doing, we're keeping that in mind as well. Any more questions? Where was I? I was here. Yes. Okay, yeah, I was talking about the residual maps. So the super resolution is staying very close to the high resolution target, which is what we want. And if you look at the median error, comparing the median error of the reconstructed super resolution and also the high resolution, we see that our the blue one, which is the reconstructed error, is staying very close to the high resolution error, meaning that from this point on, if we want to improve the performance of this model, we are bound by the observational nodes. We are no longer bound by the architecture or fine-tuning the architecture. If we want a better outcome, we should have better observational data. Another very good evaluation that we can do for making sure that the generated spectra is physical, has like physical meaning to it, is looking into the SNR of each of the lines that we're interested in looking at. We check some of the lines that are very useful for galaxy diagnostics, such as the alpha, H beta, O2 and O3. And as you can see, comparing the signals on all of our evaluation data set, comparing the signal to noise from the low resolution input and the super resolved output, we have a systematic boost in terms of the recovered signal to noise ratio. So we are gaining more details on the line profiles of each of these lines. Also, we can, as I mentioned, our middle step is redshift estimation. The whole architecture is not fine-tuned for redshift estimation. Redshift estimation is only a middle step to help with the final task of reconstruction. However, we are also doing a very good job on estimating the redshifts. Comparing the two redshifts that comes from the medium resolution of NIRSpec instrument and comparing them between the low resolution, high resolution, and our reconstructed super resolution, we see that we are doing a very good job on that term. The outlier term on a low resolution is around 16%, on high resolution is 0.5%, and our outlier rate on our reconstructed super resolution is 12.56, which is much closer to the high resolution compared to a low resolution. So it means our super resolution network is also able to do a better job in terms of redshift prediction compared to only using the low resolution. This project ended very recently, and we have started doing some new projects.
Good question. So when you calculate the redshift with yours, are you just calculating what are the outliers, or are you comparing it to ground truth that you get with the high resolution?
We are comparing to the ground truth.
Okay.
The redshift that comes from the medium resolution of the NIRSpec instrument. So it's a Spectra.
Okay.
So for the high redshift example, where does the ground truth come?
So it's basically the same CNN network that estimates a redshift run on 3 different inputs: the low resolution, the SR2 prediction, and the high resolution.
But what you call here the true redshift comes from where?
It comes from the JADES catalog, coming from the medium resolution of NIRSpec instrument.
Which is better than your high resolution here one? Or sorry,
that one is not better than high resolution. So the model, if you run the same model on low resolution, high resolution, and the SR2 in construction, and try to estimate the redshift, our SR2 estimation is much closer to the high resolution compared to the low resolution. So basically, if you are comparing each of these 3 with the ground truth.
Yeah, I guess I still don't understand where the ground truth comes from. I see how.
And so I guess they calculate the redshift. I don't know, people hear me. They probably know.
Like regression sitting and visually in spectral redshifts.
Visually.
Yeah.
Okay. So I guess the true redshift on the right one is from the high resolutions.
Yeah, they take the highest resolution in base ones, which in some cases actually even higher.
Oh, I see. Thanks.
We don't touch the ground truth at all. We just read it from the catalog of JADES. Okay, in terms of our ongoing efforts, the first one is basically we thought that, okay, JADES gives us both the spectra and photometry plus imaging. Why don't we use all of this to make sure that we extract all of the information for our reconstruction? So we are trying to expand our model to a multimodal foundation model that is specified for the task of super resolution. We have just recently started working on this. The results are not yet as good as the spectra only model, but we are working on it. The second effort is kind of a little bit
So there are existing foundation models that do this sort of, mutual multimodal learning between different modalities. I'm not sure if anyone here knows whether Ion or Astroglyph or something includes JWST spectra and images.
I don't know if it includes JADES, the JADES.
I think it's not on this. It's on STSS, I
It's
guess.
too small.
Okay. Just pointing it out because there are existing architectures that try to do this, and more data sets are being incorporated to them. So at some point, it'd be good to sort of use also that before, I guess we're all trying to work towards not having to reinvent the wheel every time. So it would be good to compare your results with something that has been pre-trained on a lot of different data sets. But anyway, yeah.
Yeah, definitely. We are kind of using the architecture from the AstroAI paper,
Mm.
something close to that, not completely that, but something closer, and we are trying to fine tune it for our specific task. So in the IM paper, the super resolution task is mentioned, but as I talked to the first author, and he mentioned that they didn't evaluate the results, so they are not sure if our super resolution is working.
To Leon.
Yeah. They're not sure if the super resolution is actually super resolving it or not. They're just making sure that it predicts it. So our task is kind of more we want to focus on the specific emission lines. So we had to fine tune the whole architecture for that task. Not just one downstream task out of many downstream tasks. So another effort that we're doing is a little bit more on the theoretical side. We wanted to make sure that what we are doing, we're using a very fancy, computationally expensive method. We wanted to make sure that this cannot be done with, some classical methods that are much less expensive in terms of computational resources. So we compared cubic interpolation, linear deconvolution, Richardson-Lucid deconvolution, and also linear plus match filter. And this one is the best one, the match filter one, obviously. And then as you can see, it is working better on some of the emission lines that we are interested in, but ours work much better in the H alpha line, in the reconstructed signal to noise ratio. However, if we look at the global reconstruction error, it is much worse for the match filter one, and our reconstruction error is much lower, and this means our method is predicting that these emission lines way better than the classical methods. Yes.
Maybe I missed something. Why would it work much better for H alpha and not the other lines?
We are not sure of that yet. Okay. This is just the work that we are still working on it, so I don't have an answer for that question yet.
That's strange, right?
That's a strange job.
Yeah.
That is something that we don't exactly understand why it's happening. But as you can see, it's working much better on the H alpha line compared to the other lines.
Yeah. Could it be something in your training set? Maybe there's no
Maybe
abundance of H alpha.
Exactly. Maybe many of the samples in our training set has the H alpha, but not all of them have H beta O2 or O2.
Yeah.
It's also H alpha is redder. And so you might have better signal noise in that region. Yeah. So you're boosting the training there.
Maybe.
So the second plot, you're just not separating categories of lines anymore. You're mixing it all together.
Yes, just getting a median error on all of the spectra.
Did you check if this is this is probably mostly because of the H alpha, right? Or I don't know. Does it correlate the signal to noise with the reconstruction?
We haven't checked that. To be honest, this is a work from just like the past week. So it's very, very new. Yeah. We haven't yet checked it. I just wanted to share with you the results that we currently have.
Right.
Yeah.
No,
And then in terms of the future perspectives of this project, obviously we can enhance this project to predict the high resolution spectra for the grism spectra from Euclid and future Roman telescope. And we hope that we can integrate this method into the pipeline of this telescope. So when we share the catalog to the public, to the community, it comes with this super resolved spectra as well. And based on the project that I just explained, we have recently put an preprint in our archive. Here is the barcode if you are interested to know more about that. And to give you a very quick summary, high resolution spectra is central to modern astrophysics. It's critical for galaxy evolution and cosmology studies. And we need it in large samples. However, it's very costly to get that. So we developed an AI model to super resolve this low resolution spectra from resolving power of approximately 100 to resolving power of 1000. And then we had to do data augmentation because we didn't have enough observational data. And the final model is able to successfully recover physical information such as blended emission lines and improve the reconstructed signal to noise ratio. And this is our team. Myself, my co-advisor at Caltech, Shubhi Hemmati, and my main advisor at UCR. And that's all.
Thank you very much, Aryana. Nice talk. Any more questions for you? Yes.
We have a lot of spectra in this resolution range from Earth-bound telescopes. How transferable is your model? Where I throw it on those?
How transferable is your model to other data sets, I guess?
It's transferable theoretically, but it needs to be tested and high performed on new data sets because the resolving power of telescopes is different, especially if you're coming from a space telescope to a NIRSpec telescope. So it needs to be enhanced again, but theoretically it is extendable.
On the note regarding the use of other potential encoders for a spectrum, I'm thinking that yes, there's been a number of models, like Cecilia was mentioning the Spander, I guess that's how it's called, that are different architectures to create summaries of the spectrum that then they use to predict redshift and things like that. There's a number of them that have been good to Spander being one of them. I think, however, with that one, that has been done for SDSS spectrum. There is not an official version of it that would work with the JWST spectra, but the architecture should be adaptable to any.
Yeah, we used it for nice surgery.
Right. So it's just a matter of adapting the architecture. You said that you're adopting a similar architecture as the AstroClip for your multimodality. Is that you're going to also sort of do the contrastive learning aspect of it? Okay. And so you're hoping to enhance the amount of information for prediction of redshift, for example, when you combine both galaxy spectrum and
because we have some photometric data in JADES that we don't have the spectral data for, so we wanted to include those as well. So we had to do that, that is that it brings closer the data that come from the same object instead of matching them ourselves. Because we usually match based on field array and edge, but we can just let the model do that.
Yeah, as I pointed out, it'd be good to see if existing, foundation models that have, already incorporate that. Always good to compare against those, depending on whether it has this particular data set. Okay, more questions, comments? Yes, Anna.
Yeah, talk a little bit about how you would expand this to Euclid and Rome, because the data that comes out of Euclid and Rome is very different from JWST, right? Where and get beautiful prism data, but Roman is gonna give us like one emission line. So how does it? Yeah, how do you think that would work?
We have started looking into the Euclid data because obviously we don't have the Roman one yet. The Euclid data, it has a much lower wavelength region compared to the 1 to 5 micrometer that we have from the data we see here. But if we find a way to infer the information, get the inference that we got from the JWST, and then use that on that specific region that Euclid has the emission line for, theoretically, we might be able to expand it.
Bill, and then
So maybe you know this, but is there a forward model to NIRSpec data such that you can make a prediction of what as built the spectrum should look like given a high resolution spectrum? So you inject a high resolution spectrum in the forward model, it predicts what the low resolution spectrum should be based upon the as built design of the instrument. And how does it compare to your predictions, right?
You mean like the simulations that simulate the NIRSpec spectra?
Yeah, it's from like the STSCI, right? Yeah.
There should be, I assume, yeah. Because
Yeah.
before each of these missions, people write papers on the simulations of the expected spectra.
Yeah.
We already have those for them.
Yeah, it'd be interesting to just compare to what your predictions are, because, as built, the designs are never perfect, but you might be able to actually tune that optimal model based upon your model, right?
Yeah, definitely.
And you can also get more data.
And you have more data, because you can simulate as much data as you want,
Yeah.
so one here, then buddy.
Did you try to repeat the same trick with stellar spectra?
Not really, no.
Are you planning to do so?
That's a possible, yes, extension as well.
You have a data set, a student who can move?
Probably yes.
All right.
Yeah, this question, so is there any reason why high resolution and low resolution spectrum must come from the same instrument, or can you?
Same resolving power, this resolving power function over the wavelength region.
I mean, you can just take like high resolution spectrum for objects that high resolution spectrum that exist for like Roman or Rubin or
You can do that, but you're adding like one more complexity for the model to predict, because you have different instruments, different resolving power. So the model has to learn that one as well, on top of the physical reconstruction for the spectral resolution.
That is possible.
It is possible. I haven't tried it, but you can definitely try it as well.
Okay, that looks like all questions. Anyone online, Josh? Nope. All right. Well, Aryana is here today and tomorrow. If someone wants to check, it's gonna be sitting in D308. On the AstroAI.
304.
304. Okay, 304. Whatever. Yeah. So please watch out. Other than that, let's thank her again for our next talk. Thank you.